They were built to be unstoppable, machines so massive, so advanced, that entire industries placed billion-dollar bets on their success. Engineers trusted the data, executives trusted the projections, and the world watched as these mechanical giants promised to reshape cities, oceans, and skylines. But behind the polished announcements and record-breaking specs, something quieter was unfolding. Warnings buried in technical reports, decisions made under pressure, and risks that didn't look dangerous until it was already too late. This is not a story about small breakdowns or routine accidents. It's about the moments when ambition outran reality, when cutting-edge machinery met conditions no blueprint could fully predict. As timelines tightened and costs rose, confidence gave way to tension, and innovation began to carry a darker edge. Because sometimes the most expensive failures don't start with a crash, they start with absolute certainty that nothing could go wrong. Billion-dollar bets that started with overconfidence. In 2001, when planners unveiled Boston's massive infrastructure overhaul known as the Big Dig, the promise sounded unstoppable. New tunnels, reduced traffic, and engineering that would redefine urban construction. The machines chosen for the project were among the most advanced tunnel boring systems ever deployed in the United States. Early projections claimed the risks were fully modeled. By 2004, however, leaks, structural defects, and ballooning costs exposed a harsher truth. The machinery was operating at limits engineers had never fully tested in real urban conditions. What began as confidence in scale slowly turned into investigations, contractor disputes, and billions added to the budget. A decade later, another high-stakes gamble unfolded in the Gulf of Mexico. The offshore drilling rig Deepwater Horizon oil spill, operating under BP in April 2010, represented a new era of deepwater extraction. The machinery was built to push further beneath the seabed than previous systems, combining complex blowout preventers, automated monitoring, and high-pressure drilling equipment. Internal reports later revealed warnings about equipment integrity and decision-making under cost pressure. When the rig exploded on April 20, 2010, the failure wasn't just mechanical. It exposed a culture where aggressive timelines and financial targets overshadowed caution. The cleanup and legal consequences would eventually cost tens of billions of dollars, transforming a technological milestone into one of the most expensive industrial disasters ever recorded. Overconfidence also defined the launch of Bertha, Seattle's giant tunnel boring machine used for the Alaskan Way Viaduct Replacement Tunnel project beginning in 2013. At 17.5 meters in diameter, it was marketed as one of the largest TBMs ever built. Officials assured the public that extensive modeling had minimized risk. But within months of operation, the machine overheated and stalled beneath downtown streets in December 2013. Engineers discovered unexpected ground conditions and component failures that required years of redesign. Costs surged while lawsuits emerged between contractors and insurers. What was meant to be a symbol of technological certainty became a frozen monument to assumptions that proved premature. Not every billion-dollar failure happens underground or offshore. In August 1991, the Norwegian oil platform Sleipner A, constructed by Statoil, sank during a controlled ballast test due to a design miscalculation linked to finite element software modeling. The collapse occurred before production even began, instantly turning a high-profile engineering achievement into a financial catastrophe estimated at around $700 million. Investigations showed that small numerical errors in structural analysis software went unnoticed during approval stages. The machinery itself didn't fail randomly. It performed exactly as designed, and that design carried a flaw no one challenged aggressively enough. These cases share a pattern that repeats across heavy industry. Early press conferences focus on scale and innovation. Contracts are signed years before machines touch real terrain. By the time engineers raise concerns, the financial momentum is already unstoppable. Cancellation becomes politically unacceptable, especially when governments or multinational investors are involved. Every additional delay deepens the commitment, locking decision-makers into defending equipment that may already be showing signs of instability. In internal meetings, language shifts subtly. Instead of asking whether a machine should exist at its current scale, teams discuss how to manage temporary anomalies. Budget revisions are framed as strategic adjustments. Technical teams are urged to find solutions without slowing deployment. The narrative changes from caution to inevitability, a psychological turning point where admitting risk feels more dangerous than pushing forward. The most expensive machinery failures rarely begin with obvious mistakes. They start with optimism, reinforced by past victories, polished presentations, and the belief that modern engineering can outpace uncertainty. Each billion-dollar bet is built on the assumption that complexity can be controlled. But history shows that when machines grow too large, too fast, or too experimental, confidence itself becomes a hidden liability, one that doesn't reveal its true cost until the first crack appears and the countdown to failure has already begun. The warning signs buried inside technical reports. Long before a billion-dollar machine fails in public, the first cracks usually appear in documents no one outside the project ever reads. Engineering logs, inspection summaries, vibration analyses, pages filled with cautious wording that hint at problems without sounding like alarms. In many of the most expensive heavy machinery failures ever recorded, the warnings were not hidden. They were written down, time-stamped, and filed away. Months before the April 20th, 2010 explosion that triggered the Deepwater Horizon oil spill, internal testing and contractor reports raised concerns about the rig's blowout preventer and cement integrity. Technical staff noted abnormal pressure readings and inconsistencies during well stability checks in early 2010. None of these reports said catastrophe. Instead, they used familiar industry language: manageable risk, acceptable deviation, operational workaround. Inside the system, that phrasing mattered. It meant the machine could keep operating while engineers debated solutions. Outside the system, it meant no one realized the warning signs were already stacking up. A similar pattern emerged during the Big Dig tunnel project in Boston throughout the late 1990s and early 2000s. Inspection reports from 1999 to 2003 documented issues, with ceiling panel anchors, water infiltration, and material fatigue. Engineers flagged adhesive strength concerns years before a fatal tunnel collapse in July 2006 drew national attention. The data existed: load tolerances, humidity effects, structural stress models, but each issue was treated as an isolated maintenance task rather than a systemic machinery and design failure. Technical reports rarely sound dramatic. They accumulate quietly until one day they read like a timeline everyone wishes they had taken more seriously. Seattle's massive tunnel boring machine, deployed for the Alaskan Way Viaduct Replacement Tunnel project, tells another story about buried warnings. During early excavation in 2013, sensors detected rising temperatures and abnormal torque resistance. Daily machine logs recorded cutter head stress levels that exceeded projections. By December 2013, the TBM stalled completely. Investigations later revealed that soil composition and steel pipe obstructions had been underestimated in early geotechnical reports. The warning signs were technical, precise, and easy to overlook if you weren't reading every page. To the public, the machine stopped suddenly. To engineers reviewing the data months later, the shutdown looked almost inevitable. Even projects that fail before entering full operation often leave a trail of overlooked signals. The Sleipner A platform collapse on August 23, 1991, traced back to finite element modeling errors that produced inaccurate stress calculations. Engineers had relied heavily on simulation outputs generated in the late 1980s, trusting software assumptions that underestimated structural shear forces. Internal documentation showed minor discrepancies between predicted and measured stresses during preliminary tests. Those discrepancies were noted, but not escalated as critical risks. When the platform sank during a controlled ballast test, the investigation revealed that the technical evidence had been present all along, buried in calculations few decision-makers fully questioned. Why do these warnings stay buried? Part of the answer lies in how engineering culture communicates risk. Technical reports prioritize precision, not urgency. A phrase like "within tolerance" can hide a wide margin of uncertainty. Engineers often avoid alarmist language unless failure is certain, while project managers focus on schedules and budgets that leave little room for reinterpretation of data. The result is a slow normalization of anomalies. Small deviations become routine entries in maintenance logs instead of signals demanding a halt. Another factor is scale. Modern, heavy machinery produces enormous volumes of telemetry data, pressure readings, thermal maps, software diagnostics, structural strain metrics. When a project spans years and involves multiple contractors, responsibility for interpreting that data becomes fragmented. One team monitors hydraulics, another oversees automation software, another handles structural integrity. Each sees only a piece of the puzzle. Without a unified risk narrative, warning signs remain technical footnotes instead of strategic red flags. Sometimes, the most revealing lines in a report appear only after failure, when investigators compare early documents against final outcomes. A vibration spike that seemed minor in January becomes a clear precursor when viewed alongside a catastrophic breakdown months later. A maintenance delay justified as cost efficiency suddenly reads like negligence. The documents themselves never changed, only the context did. In billion-dollar machinery projects, disasters rarely begin with a single dramatic moment. They begin with quiet entries in engineering databases, time-stamped observations that feel too small to stop the momentum of a massive investment. By the time executives or the public recognize the significance of those warnings, the machine is already in motion, and the technical reports that once whispered caution have become evidence of how early the signs truly appeared. Design rooms are controlled environments. Simulations behave predictably. Materials perform according to specification sheets, and timelines move forward in clean, logical phases. But the true test of any billion-dollar machine begins the moment it leaves theory and collides with terrain, pressure, weather, and human decision-making. That transition, from controlled engineering to uncontrolled reality, is where some of the most expensive, heavy machinery failures truly begin. On April 20, 2010, the drilling systems aboard the Deepwater Horizon oil spill were operating nearly 1,500 meters above the seabed in conditions far more volatile than early models suggested. Deepwater drilling equipment had passed numerous tests, yet real ocean pressures exposed vulnerabilities that simulations underestimated. Mud circulation patterns behaved unpredictably, and sensor readings fluctuated as the well entered unstable geological zones. Engineers faced a familiar dilemma: stop operations and risk massive financial delays, or continue while troubleshooting in real time. Reality didn't wait for consensus. When methane surged through the system that night, the machinery was pushed beyond the margin engineers believed they controlled. Urban tunneling offers another example of theory colliding with the unexpected. When the massive boring machine known as Bertha began work in July 2013 for the Alaskan Way Viaduct Replacement Tunnel Project, project planners relied heavily on geological surveys conducted years earlier. Models predicted consistent soil density beneath downtown Seattle. Instead, the machine encountered steel pipes, mixed fill layers, and abrasive ground conditions that caused overheating and excessive cutterhead wear within months. By December 2013, Bertha stalled completely. What looked like a mechanical failure was actually the moment reality invalidated assumptions embedded deep inside early planning documents. The machine wasn't defective in isolation, it was operating in an environment far more hostile than designers expected. The same clash between expectation and environment shaped Boston's Big Dig during the late 1990s and early 2000s. Tunnel construction machinery was designed for predictable excavation cycles, yet groundwater seepage and aging urban infrastructure introduced variables no blueprint could fully capture. As crews advanced through dense city layers, equipment faced corrosion, vibration stress, and alignment issues caused by shifting soil conditions. Machinery that performed flawlessly in controlled tests struggled once exposed to decades-old foundations, hidden voids, and inconsistent materials beneath active highways. Each adjustment required redesigns, pauses, and emergency engineering decisions that drove costs higher. Even offshore structures face a similar confrontation with reality. When Norway's Sleipner A platform underwent ballast testing on August 23, 1991, the expectation was a routine verification phase before production began. Instead, real-world hydrostatic pressures revealed a structural weakness overlooked during modeling. As water filled the ballast tanks, stresses concentrated along thin concrete walls until the platform suddenly sank. The collapse demonstrated a brutal engineering truth. Simulations can predict behavior, but only reality confirms whether those predictions were correct. One reason this stage becomes so dangerous is psychological. By the time machinery reaches deployment, billions have already been spent. Teams are less willing to interpret anomalies as existential threats because acknowledging fundamental flaws could halt the entire project. Instead, unexpected resistance or performance drops are reframed as startup challenges. Engineers tweak parameters. Operators adjust workflows. Management pushes forward, convinced the machine only needs minor calibration to match its promised capabilities. Field conditions also introduce human factors absent in early testing. Operators work long shifts under production pressure. Maintenance crews improvise when spare parts are delayed. Software designed in laboratory conditions interacts with unpredictable operator inputs and changing environments. These real-world dynamics amplify small design limitations into serious operational risks. A hydraulic system that tolerates minor overheating in tests may degrade rapidly when exposed to dust, salt water, or continuous load cycles far beyond initial projections. What makes this phase especially costly is visibility. Once a massive machine is deployed, beneath a city, offshore, or deep in a mining operation, fixing problems becomes exponentially more complex. Components can't simply be swapped in a workshop. Entire work zones may need to be excavated or shut down. Each hour of downtime compounds financial losses, turning technical miscalculations into economic crises. When the machine meets reality is rarely a single dramatic moment. It's a slow realization that the world refuses to behave like a model. Sensors begin to drift outside normal ranges. Production targets slip. Teams hold emergency meetings to reinterpret data that once seemed certain. And somewhere between the first unexpected vibration and the first full shutdown, a project built on confidence begins to confront the possibility that the machine was never ready for the world it was meant to conquer. The most expensive phase of any heavy machinery failure rarely begins with an explosion or a collapse. It begins with silence. Engines stop. Production targets freeze. Crews wait beside machines that were supposed to run continuously, while every hour offline quietly burns through millions in lost revenue. Shutdowns transform technical problems into financial crises, exposing just how fragile billion-dollar timelines really are. After the April 20th, 2010 disaster that ignited the Deepwater Horizon oil spill, the shutdown didn't affect just one rig. Entire drilling operations across the Gulf of Mexico slowed or halted as regulators enforced new safety reviews. Machinery worth billions sat idle, while companies calculated daily losses and deferred production. For operators, the cost wasn't limited to repairs. It included halted supply chains, stranded vessels, and insurance disputes that dragged on for years. Each delay created a ripple effect, turning a mechanical failure into a long-term economic wound. Urban megaprojects show a different version of financial bleeding. When Seattle's massive boring machine stalled in December 2013 during the Alaskan Way Viaduct Replacement Tunnel project, crews couldn't simply pull the machine out for repairs. Entire sections of the city became construction bottlenecks. Contracts had to be renegotiated, redesigns approved, and access shafts excavated just to reach damaged components. Months turned into years. Every delay forced taxpayers, contractors, and insurers into a complex battle over who would absorb the rising costs. The shutdown wasn't a pause. It became a slow drain that reshaped the project's entire financial structure. Boston's Big Dig revealed another layer of how delays escalate. As machinery struggled with water leaks and structural alignment issues in the late 1990s and early 2000s, project managers faced an impossible balance between safety and deadlines. Each repair cycle required traffic reroutes, night shifts, and emergency inspections that multiplied labor expenses. The longer machinery operated under imperfect conditions, the more secondary problems emerged: corroded components, misaligned panels, and increased maintenance intervals. Budget revisions became routine, and public trust eroded as projected completion dates slipped further away. Shutdowns also expose internal tensions that were hidden during active production. When a machine stops generating revenue, executives begin scrutinizing every design decision that led to the delay. Engineering teams are asked to justify tolerances approved years earlier. Contractors argue over maintenance responsibilities. Legal departments enter the conversation long before the machinery is fixed. In many cases, the cost of arguing about the shutdown becomes almost as significant as the cost of repairing the machine itself. One of the most damaging aspects of prolonged delays is uncertainty. Investors and stakeholders can handle bad news if it arrives with a clear timeline. What destabilizes projects is the absence of a predictable recovery path. When engineers cannot guarantee whether a repair will take weeks or years, financial models collapse. Equipment leasing agreements expire. Insurance premiums spike. Suppliers hesitate to deliver parts without revised contracts. A machine that once symbolized efficiency becomes a financial liability simply because no one can say when it will run again. Even the act of restarting a halted system introduces new risks. After months of inactivity, hydraulic fluids degrade, electronic systems require recalibration, and structural components experience stress redistributions. Restart procedures become slow and cautious, further extending downtime. Operators who once ran the machinery daily must retrain to handle updated safety protocols. Each attempt to resume operations carries the fear that another shutdown could follow immediately, compounding losses. Public perception adds another layer of pressure. Media coverage often focuses on daily cost overruns, turning technical delays into political issues. Government-backed projects face hearings and audits. Private companies see stock prices fluctuate with every update. The machinery itself becomes a symbol, not of innovation, but of financial miscalculation. What makes shutdowns particularly devastating is that they rarely feel dramatic from the inside. There is no single moment where everyone realizes the damage is irreversible. Instead, costs accumulate quietly. An extra week of labor here, a new inspection requirement there, another redesign proposal waiting for approval. Over time, the financial bleeding becomes harder to hide. Reports begin to use phrases like unrecoverable schedule impact or indefinite delay, signaling that the project has moved beyond simple troubleshooting. In the world of expensive, heavy machinery, failure doesn't always look like destruction. Sometimes it looks like a silent construction site, a motionless drilling platform, or a tunnel machine frozen beneath a city. The engines are off, but the costs keep running, and with every passing day, the gap between what the machine promised and what it delivered grows wider, turning technical setbacks into billion-dollar consequences. Secrets, cover-ups, and internal conflict. When billion-dollar machinery begins to fail, the technical battle is only half the story. Behind meeting room doors and encrypted email threads, another struggle unfolds, one shaped by liability, reputation, and the fear of being blamed for decisions made years earlier. In many of the most expensive heavy machinery failures ever recorded, the loudest conflicts never happened in public. They happened internally, where engineers, executives, contractors, and regulators clashed over what should be revealed and what should remain buried. In the months leading up to the April 20th, 2010 disaster tied to the Deepwater Horizon oil spill, internal communications revealed tension between operational speed and safety caution. Investigations later pointed to disagreements over cement testing results and pressure anomalies. Engineers raised technical concerns using measured language, while decision-makers weighed the financial consequences of halting operations. Emails and reports showed that risk wasn't invisible. It was debated, reframed, and sometimes minimized as teams tried to keep schedules intact. After the explosion, those same documents became evidence, reshaping public perception of whether the catastrophe was an accident or the outcome of ignored warnings. Urban megaprojects reveal a different kind of internal conflict, one driven by contracts and political scrutiny. During Boston's Big Dig, disagreements surfaced over material quality, inspection procedures, and responsibility for maintenance failures. Contractors blamed design specifications. Designers pointed toward installation practices. Oversight agencies struggled to determine who had authority to stop the work. Technical reports circulated through multiple organizations, each interpreting the data in ways that protected their own role in the project. The result was a fragmented narrative where no single group fully owned the risks building beneath the city. Seattle's stalled boring machine in the Alaskan Way Viaduct Replacement Tunnel project became another example of how internal disputes escalate once machinery stops moving. After the machine overheated in December 2013, legal teams quickly entered the engineering conversation. Contractors argued that unexpected ground conditions caused the failure, while project owners questioned whether the machine's design could withstand real-world stress. Behind the scenes, negotiations focused on insurance claims and cost responsibility long before the public understood the technical details. Each statement released to the media was carefully worded, revealing only fragments of a much larger conflict over accountability. Secrets in these projects rarely take the form of dramatic conspiracies. More often, they emerge from ordinary corporate behavior, selective reporting, cautious legal language, and internal reviews that remain confidential. Engineering teams might draft detailed analyses that never reach executives outside the project. Risk assessments may be shared under non-disclosure agreements, limiting who can act on the information. Over time, the organization itself becomes divided into silos, where one group understands the severity of a problem, while another continues presenting optimistic forecasts to investors. The pressure to control information intensifies when billions of dollars are at stake. A public admission that a machine's core design is flawed can trigger lawsuits, regulatory shutdowns, or stock market reactions. As a result, companies often frame problems as temporary setbacks rather than structural failures. Maintenance issues become optimization phases. Safety concerns become operational reviews. This language doesn't necessarily hide the truth, but it softens it, delaying the moment when decisive action might prevent further escalation. Internal conflict also affects morale. Engineers who document repeated anomalies may feel ignored when leadership focuses on deadlines. Operators working alongside unstable machinery sense tension long before official announcements acknowledge risk. Teams begin protecting their own decisions, keeping personal records of conversations and approvals in case investigations begin later. The project shifts from collaboration to self-preservation, where every technical debate carries legal implications. Once investigations start, hidden documents often reshape the narrative. Meeting notes reveal disagreements that never appeared in public statements. Early test results show that warning signs existed long before shutdowns or accidents occurred. What looked like a sudden failure becomes a slow accumulation of unresolved conflicts, each one recorded somewhere in a technical archive. In the world of expensive heavy machinery, secrecy doesn't always come from malicious intent. It grows from complexity, from dozens of contractors, overlapping responsibilities, and the fear that acknowledging uncertainty could bring everything to a halt. But when failures finally surface, those internal conflicts leave a permanent mark. The machines may stop operating, but the arguments over who knew what and when often continue far longer than the machinery itself ever ran. Lawsuits, insurance wars, and public fallout. When billion-dollar machinery fails, the technical story quickly gives way to something colder and far more complex: legal strategy. Engineers step back while lawyers, insurers, and regulators move in, turning mechanical breakdowns into years of courtroom battles. Contracts written long before the first bolt was tightened suddenly become the most important documents in the entire project. After the April 20th, 2010 catastrophe tied to the Deepwater Horizon oil spill, legal fallout spread across multiple continents. BP, Transocean, Halliburton, and several subcontractors faced overlapping lawsuits over liability, environmental damage, and operational decisions made in the final hours before the explosion. Insurance carriers challenged claims worth billions, arguing over whether equipment failure, human error, or corporate negligence triggered the disaster. By 2015, settlements and penalties had reached tens of billions of dollars, making it one of the most expensive legal battles ever linked to heavy industrial machinery. Urban infrastructure projects reveal a slower but equally brutal version of legal conflict. During Boston's Big Dig, structural problems and cost overruns led to years of litigation between contractors, suppliers, and government agencies. When a fatal ceiling collapse occurred in July 2006, lawsuits expanded to include questions about adhesives, inspection procedures, and design approvals dating back years. Insurance companies resisted large payouts, arguing that certain failures fell outside policy coverage because they were tied to long-term design flaws rather than sudden accidents. The result was a drawn-out legal environment where engineering decisions were dissected line by line in courtrooms instead of laboratories. Seattle's stalled boring machine in the Alaskan Way Viaduct Replacement Tunnel project triggered another wave of insurance disputes. After the TBM overheated in December 2013, project owners and contractors argued over whether the breakdown was caused by unforeseen ground conditions or by mechanical design limitations. That distinction mattered enormously. If the environment caused the damage, insurers might cover repairs. If the design was flawed, liability could shift back to manufacturers or contractors. Years of negotiations followed, with each side presenting technical analyses to support its version of events. Insurance wars often become more expensive than the repairs themselves because they slow every decision. Before parts can be replaced or construction resumes, insurers may demand independent investigations, forensic engineering reports, and third-party audits. Each new analysis delays progress while legal teams evaluate how findings might affect liability. Projects enter a state of limbo where machinery remains idle, not because engineers lack solutions, but because no one wants to authorize work that could weaken their legal position. Public fallout grows alongside these disputes. Media coverage transforms technical disagreements into headlines about corporate negligence or government mismanagement. Politicians call for hearings. Shareholders question leadership decisions. For publicly funded projects, taxpayers demand accountability, turning engineering setbacks into political controversies. Companies must balance transparency with legal caution, releasing statements carefully crafted to avoid admitting fault while still reassuring the public that progress continues. The reputational damage can be as costly as any settlement. After major machinery failures, companies often face stricter regulatory oversight, higher insurance premiums, and reduced investor confidence. Even suppliers who played minor roles may struggle to secure future contracts if their names appear repeatedly in legal filings. Inside the industry, risk managers begin rewriting contract clauses to avoid similar exposure, reshaping how future machinery projects are financed and insured. Another complication comes from international jurisdiction. Offshore platforms, cross-border infrastructure, and multinational construction teams create overlapping legal systems that slow resolution. One court may focus on environmental impact, another on contractual liability, and another on worker safety violations. Years can pass before a final financial picture emerges, long after the machinery itself has been repaired or abandoned. In the end, lawsuits and insurance battles redefine the narrative of failure. What begins as a technical problem becomes a financial chess match where every email, maintenance log, and engineering report turns into potential evidence. The machine that once symbolized innovation fades into the background, replaced by negotiations over percentages, responsibility, and compensation. And while the public often remembers the dramatic moment when a project collapsed or stalled, the true cost continues to grow quietly in legal filings. A reminder that in heavy industry, the consequences of failure don't end when the engines stop running. The aftermath without redemption. The aftermath without redemption. When the cameras leave and the court filings slow down, what remains is often the most uncomfortable part of a billion-dollar machinery failure, the silence that follows. No triumphant recovery, no dramatic comeback, just abandoned equipment, altered skylines, and balance sheets permanently scarred by decisions that can't be undone. In heavy industry, not every project gets a heroic ending. Some simply stop, leaving behind consequences that linger long after the machines themselves disappear. In the years following the April 20th, 2010 disaster tied to the Deepwater Horizon oil spill, the physical wreckage of the drilling rig sank beneath the Gulf of Mexico, but the financial and environmental aftermath refused to fade. Cleanup vessels withdrew, headlines shifted. Yet, communities and ecosystems continued to deal with the long-term effects of the spill. For the companies involved, settlements and restructuring efforts reshaped corporate strategy for more than a decade. The machinery that once symbolized technological ambition became a cautionary reference, not a legacy of innovation, but a reminder of irreversible cost. Urban megaprojects carry a different kind of aftermath. Boston's Big Dig eventually reached completion, yet the controversies surrounding equipment failures, budget overruns, and safety incidents never fully disappeared. Investigations left a trail of revised regulations and public skepticism toward future mega construction plans. For many residents, the finished tunnels did not erase memories of years of disruption or the loss tied to structural failures. The machinery moved on, but the perception of risk stayed embedded in public discourse. Seattle's stalled boring machine during the Alaskan Way Viaduct Replacement Tunnel project also illustrates how aftermath can feel unresolved even after work resumes. When repairs finally allowed tunneling to continue years after the initial shutdown, the narrative had already changed. Instead of celebrating technological progress, the project became shorthand for delay, dispute, and inflated costs. The machine completed its mission, but the sense of overconfidence that defined its early launch never fully recovered. What makes these endings feel without redemption is the way financial consequences outlast physical fixes. Companies involved in major machinery failures often restructure divisions, sell assets, or shift focus to less risky ventures. Insurance premiums rise. Investors demand stricter oversight. Engineers who worked on the projects carry lessons into future designs, but those lessons are shaped by caution rather than triumph. Even when infrastructure eventually functions as intended, the original vision, faster, cheaper, revolutionary, fades under the weight of what went wrong. Workers and communities also experience a quieter aftermath. Construction crews who spent years alongside stalled machinery move on to other projects, leaving behind half-finished landscapes that slowly transform into ordinary parts of the city. Offshore crews return to redesigned rigs operating under stricter rules. Suppliers who once invested heavily in specialized components shift toward more conservative contracts. The industry adapts, but rarely celebrates these changes. They emerge from loss, not success. Perhaps the most lasting consequence is psychological. Future proposals for massive machines face tougher scrutiny because past failures never truly disappear from memory. Engineers double-check assumptions. Regulators demand deeper testing phases. Investors hesitate before approving projects that promise revolutionary scale. The ghosts of previous breakdowns shape decisions long before new machines ever reach construction sites. In the end, the aftermath of expensive heavy machinery failures is rarely dramatic. There are no cinematic finales, only lingering questions about what might have been prevented if warnings had been taken more seriously or ambitions scaled more cautiously. The machines themselves may be dismantled, repaired, or replaced, but the financial scars remain embedded in corporate histories and public trust. And that is the harshest reality of all. Some billion-dollar bets don't end with lessons that feel inspiring or redemptive. They end with quieter outcomes, revised contracts, stricter regulations, and the knowledge that the world moved forward not because the machine succeeded, but because everyone involved learned to live with the cost of failure.